Hello.
Morning.
Morning.
Hi, good morning.
Hi. All right, so let's get started. This week we did not have a Diva War meeting, but we did have an open source meeting, and I thought it was a good open source meeting for the first coding period. We had reports from all three Google Summer of Code scholars, and Jesse also had a nice feature on knowing when to ask questions and knowing when to read the documentation or the manual. And, the other things in organizational project management and things like that. So that was nice. Jesse's been hard at work writing up his ideas, his project management stuff. Seems like now that he's graduated from his program, he's, catching up, making up for lost time. So that's good. And I talked about a paper that the Active Inference Institute will be featuring soon in a live stream. So we'll maybe be involved in that or check that out. So why don't we get started with a few features here? So the first thing I wanted to talk about today is this article. Michael Skuhersky, I think, is a person from MIT. And the title is "We Can, Must, and Will Simulate Nematode Brains." And so it's written kind of in the way that's kind of a history of nematode brain simulation, which seems like a niche area, but the idea is that everything has failed and he wants to try it again. And I think that's kind of the way a lot of people have thought about it, even though, as the article shows, people have made incremental progress on it. So, this is kind of setting up, motivating why you would want to do this. A near perfect simulation of the human brain would have profound implications for humanity. It could offer a pathway for us to transcend the biological limitations that have constrained human potential and enabled unimaginable new forms of intelligence, creativity, and exploration. This represents the next phase in human evolution, freeing our cognition and memory from the limits of our organic structure. And so the idea is that it's, for a number of reasons, it's not something we can attain right now. We can't really reverse engineer things, but we can build up from very simple nervous systems. And so that's kind of the motivation behind simulating C. elegans. And so the idea is that, we have these simple movements or these stereotypical movements that are created by smaller circuits that we can identify and we can simulate and we can understand how they work in totality. Okay, so this kind of goes through the history of worm brains. So one of the advantages of the C. elegans model is that you have the full connectome, and that was derived rather early. It was in 1986 when they really kind of had this complete connectome map drafted, and so that that was pretty early in the scheme of connectomics. I mean, we have gotten other connectomes since then. We've talked about the fly connectome, Drosophila connectome before, and this was in a time before they really applied computing power to it. So this was a very simple operation to map out 302 neurons, and by simple I mean sitting beside a microscope and doing a lot of the work, the annotation work, the drawings manually. So this is all kind of the sort of the earliest work on connectomes. And so, uh, people started to apply computing to C. elegans. They used a lot of the things that were built up in the community beforehand. So Sidney Brenner, of course, was the first person to propose using C. elegans as a model organism in the 1960s. And so once that started, you had people like Solston and White, and they were able to work out some of these details of these systems, these cellular systems. And so Ernest Niebur and Paul Erdos kicked things off with a biophysical model of nematode locomotion in 1991. If you're familiar with the story of Paul Erdos, he's the mathematician who famously would wander around with a suitcase collaborating with people. And so there's the Erdos number in citation networks, which is like, how close are you to Paul Erdos? And people, might be 2 or 3 steps away from Erdos. Some people are 1, they published with him, which is an interesting aside. So that, we had this sort of biophysical model in 1991, offered in this paper here, which is the theory of the locomotion of nematodes. And so, you have Ernest Niebur and Paul Erdos, so you have this sort of mathematical or computational flavor to it. It's published in a biophysical venue, but it's also, you have to kind of think about some of these kind of computational problems, mathematical problems in these kind of simulations. So that was in 1991. Then 2 different teams, one at the University of Oregon, the other in Japan, published plans for building more ambitious models in the late 1990s. So neither of these projects got off the ground, but in 2004, the virtual C. elegans project at Hiroshima University got somewhat farther. So they released 2 papers describing their model, which simulated the nematode's motor control circuits. So these papers are, this one is a model of motor control of the nematode C. elegans with neuronal circuits. And so this is in artificial intelligence in medicine, and they proposed this neuronal circuit for motor control. The simulated nematode could respond to virtual pokes on its head, but it didn't do much else. And even this was arguably not a true simulation. And so that's where things stood until the dawn of the 2010s, and then they get in here into OpenWorm and the history of OpenWorm, kind of getting into the origins of OpenWorm, which involve Giovanni Edili, and he actually was tweeting from the Twitter account of the Whole Brain Catalog, and this is a project to consolidate data from mouse brains. And Stephen Larson, of course, who was at the time a neuroscience grad student at UC San Diego, decided to hook up with Edili and start OpenWorm and get some other people involved as well. So I actually joined OpenWorm a little bit later than this, but the origins were kind of in 2010, 2011. So it's that's when it started. The original vision behind OpenWorm was that the efforts of a decentralized group of academics with the goal of creating a complete, realistic, and open source model of C. elegans. And so, yeah, there was a lot of press around that. Of course, you make these. So, yeah, you make these predictions that probably won't come true, but people make them anyways. So David Dalrymple was working on a parallel project at MIT, which he dubbed Nemalode, which I've never heard of, which maybe is kind of the point here. OpenWorm scientists largely use data from dead nematodes, but Dalrymple wanted to use the then new technique of optogenetics to study living specimens. In a 2011 comment on Less Wrong, Dalrymple wrote, "I would be extremely surprised, for whatever that's worth, if this is still an open problem in 2020. So it's now 2025, and nematode simulation remains an open problem. Dalrymple abandoned Nematode in 2012. OpenWorm still exists, but has not made substantial progress over the past 10 years, where it's creating a truly scientific whole brain simulation due to lack of available data. But of course, there have been a lot of tools that have been created. But in any case, so I mean, I guess you could say, yeah, we still have this as an open problem. On the other hand, it seems like this is a problem that's always off into the future, because people's demands are kind of like, I guess I want to see something that's kind of like, I don't know, more than what we have. It's really kind of a hard standard, mainly because there's no concrete standard to work towards in the first place. It's kind of a visionary thing. But anyways, so the author here mentions, we're not quite back to where we were in the 2010s. We have much better data on the C. elegans nervous system and, as I'll discuss later, much better tools to study it. But we aren't much closer to simulating the whole brain. So where we got stuck, of course, he mentions the Human Brain Project and Harry Markram, and how that was, I guess, seen as a failure. Of course, we've talked about the Human Brain Project a number of times in the group, and how it wasn't particularly a failure. And then, of course, defining this definitional problem is important, because, we have to kind of say what we're looking for. And I guess that's the most important part. Otherwise, we could just be working towards something that we could always say we never achieved. Or we could always say we achieved it if we just change the definition post hoc. And so we don't really want to do that. We want to have a good definition of simulation. So this person's view is that a good simulation of a nervous system is one that both accurately replicates its functionality and reliably predicts the future activity of a real system under the same initial conditions. So this is saying that a simulated nematode and a simulated plate of agar, which is what they typically use in experiments, you put the worm on this agar plate, or this surface, which is an agar gel, and you put food on top of it, and the worm lives out its life on this slab of agarose. And so whatever the nematode can do there, the simulation should produce behaviors that reflect that, or that are basically the same. Of course, the interesting thing here is that agarose is not the nematode's native environment. Their native environment is this three-dimensional environment in the soil, but that's neither here nor there for I guess the purposes of this definition. If we disturb the simulation, say, by poking or shining a light on it, it should respond the same way the real nematode would. And it should keep acting like a real nematode over time, instead of accumulating more error as time goes on. Which I don't know what that means, because I don't know that, like, real nematodes don't accumulate more error, but whatever. This definition can help us clarify what is and isn't simulation. Last October, a consortium of scientists across 127 institutions published the complete connectome of the fruit fly. So we've talked about this. This involves this flywire project and the flywire connectome. And so, this is something that is, of course, a data set. It's rekindled the interest in brain simulation. And in a sense, the flywire connectome can be used to simulate a fruit fly. When Philip Hsu, a researcher on the project, test-fired the neurons responsible for sensing sugar, the model predicted that other neurons that extent the fly's proboscis would fire as they would in a real fly. Other researchers have since used Hsu's model to accurately predict neural patterns involved in the fly's sense of taste, grooming, and location. So this is not, I guess not really a simulation. Again, we're playing with this definition, and maybe trying to realize a definition that can't be realized, because this might be, in an academic sense, this might be a very good example of a simulation. But I guess it isn't. Maybe this person is thinking more of emulation too, which of course we've talked about with some of the people interested in human brain emulation and whole brain emulation, which we can talk about that later in terms of what we think about that. But this previous study that I mentioned, Philip Shu's study, which we talked about in the group a while back, Shu himself has been clear that the model is extremely simplified and makes assumptions about key parameters governing how neurons behave. When the model can successfully predict the behavior of particular groups of neurons, it cannot mimic the exact functionality of an entire fly brain. True, but you can simulate different aspects of the brain and behavior, which is maybe more tractable. That's because the flywire model is missing the same thing as openworm, as well as other attempts to simulate nematodes. Good data on the relationship between neural structure and neural function. So that's where we're getting at, this sort of relationship between structure and function, which, again, I don't know what I guess the idea is that you can do this with magic optogenetics or something, or that there's some magical method that you can use to gain this information. And of course, if you think about this, maybe as other people do, maybe outside of this community, maybe people like an embodiment, the argument that is basically that function is emergent from structure. That is, it's going to be really hard to predict any specific function, maybe even in C. elegans. And so, it's kind of an interesting point. I'm not really sure, if, I guess the implication here is that you haven't cracked the code unless you really have that map. And what I'm saying here is that maybe you can't have that map directly. Maybe it's something that is, you just have to approximate and hope for the best. So it's not just definitional, the problem here. It's maybe expectationally as well. Okay, this is a really interesting article. It kind of gets into a little bit more about collecting data and getting new types of data, bringing them to bear, getting higher resolution in microscopy, and some of the other techniques that we can use to look at the function of neurons. So you can look at the cells themselves and their location and their contents. In other words, what are their ion channel profiles? What are the connections? And of course, we have some of those data, and we're getting more data all the time, as you do in science. And so because you have 300 neurons or so in C. elegans, that makes that tractable. So you can catalog all of that. You can then build a model, you can simulate the model, etc. And then, of course, there's this goal of producing mathematical equations or formulas that can explain the data. And this is where sort of this distinction comes into play between, can we predict behavior with like regression models, or do we have to just kind of assume that these things are emergent and build simulations that can maybe produce some of these behaviors and just leave it at that? So, this is kind of, I don't know. So this person is currently founded a nonprofit research based on research institute focused on brain simulations. So it's very interesting in the way that kind of it goes over the history here. And think about, like, one of the things openworm has done, of course, is build a bunch of tools. And what's interesting is, like, outside of the community, it would be nice to see people apply these tools and build onto these tools for simulation, but you don't necessarily see that. It's just like kind of this attitude of, well, if you failed, I'm going to have to throw that away and start over. And, it's just kind of, I guess there's like this, I'm going to say lack of vision, but there's sort of like this, like, I guess goes back to the definitional thing, where you have this definition of what you want out of a simulation. It maybe really mean more like an emulation, but then, we don't know how to achieve that. Maybe we can achieve that, but it doesn't matter because that's sort of the standard we want. And we're going to kind of define things as we go along. So everything that comes along is not really cutting it. And, I don't know. Well, we'll see how this works out in the future. And it's worth noting also that OpenWorm, there have been a lot of papers produced kind of around OpenWorm. Like, sometimes we'll cover these in the meetings where, they'll have some new technique that people who have been involved in OpenWorm in the past and kind of using sort of that way of thinking about the nematode connectome. And, there's been a lot of interesting stuff coming out on like the connectome and the function of the connectome, and the neurophysiology of the connectome. So there's a lot of interesting stuff there to follow up on. And as for the title, we can, must, and will simulate nematode brains. I mean, I guess we can. I would argue we can now. It's just a matter of like, is it really kind of matching every behavior we can observe, which is, of course, with simulations, a tough question. We must, I guess we must in the sense that if we want to simulate brain and behavior at all, that would be the first target. And we probably want that for reasons having to do with C. elegans being a model organism. And then that's up to people in the future, I guess, is to drive that research program forward. All right. Looks like Jesse's here. Welcome, Jesse. So that's okay. Now, the second thing I wanted to show, this is really interesting. This is something I think that Morgan posted in the Slack in one of the channels. This is something called genetic voids, and this is by Attention Mech. So this is a nice little simulation. I think I showed a notebook last week where they were, mathematically modeling some meshes and shapes and things like that. This is actually a simulation that runs off of GitHub.io. So this is modeling these voids. And so voids are these computational agents that, you usually have a population of voids. And they can exhibit collective behaviors. So each one of these dots is a void. And you have these populations of voids that flock together and produce these collective behaviors. And they produce the collective behaviors by sort of interacting with each other, but individually having a set of rules that they implement locally. So each void will implement a set of rules determining how close they get to one another, how far they're allowed to get from one another, rules for acceleration and velocity. And then all the voids in the collective in the population are doing this at the same time. So each void is observing its nearest neighbor. But if you do that in parallel, you have this sort of mass of behavior that, sometimes if you're at sort of the core density of the population, that can have one set of effects. Sometimes if you're on the periphery of the population, that can have another set of effects. And of course, you can implement things like steering and other types of responses from the collective, from the flock. So you can see in these flocks that you have, they're kind of, some of them are recombining, some of them are avoiding obstacles. They're kind of floating through space here, the space, and so some of them are colliding, some of them are joining each other. Notice that they're forming all sorts of interesting looking shapes and patterns, and that's actually one of the things that really sparked people's interest in voids, was that they not only can exhibit this collective behavior, but that the collectives themselves have these interesting kind of forms and shapes that they take on. So, like, you can see that there's merging behavior, there's kind of a steering behavior, and there's collision, but the collisions, of course, aren't immediate. You can steer away from each other. So it's really interesting, and this is something we played around with a little bit in terms of developmental Bradenburg vehicles several years ago. But there's a lot of, I think, really interesting research questions having to do with these kinds of flocks of voids and the shape of the flocks and the shape of the collective behavior. And what's driving that underneath? Is it something that's purely an epiphenomena? Is it purely emergent behavior? Or is there something in sort of the local control that's mapping the global control that's controlling these shapes? In other words, in a lot of the collective behavior research in birds, they find that birds can kind of maintain flock shape. And they do this through not just having simple rules, but they have sensory systems that are a little bit more sophisticated than force feedback or some sort of single signal. And so you can get these sorts of behaviors in flocks. And so can you replicate this in voids, and what's the significance of it, and what can we say about collective behavior in that way? So with voids, I just wanted to point out that we kind of maybe suffer from the same problem as we do with brain simulation, as mentioned in the last article. And that is, voids model bird flocks, mainly. I mean, they model all sorts of collective behavior, like fish schools and insect swarms. But they mainly model bird flocks, so that's what they're supposed to be modeling. And, you can match up voids and bird flocks and observe their behavior, and they look very similar, right? I mean, they look like bird flocks, but they're not really bird flocks. So the question is, are we really simulating that collective behavior or something similar? Well, in this simulation, we have a number of parameters here we can play with. So we have a population that we can set, so we can start minimally. So we can have a small population, we can have a medium population, and a standard population of 1,000. And so as we increase the number of voids in the simulation, the denser everything is, the more flocks and interchanging flocks we observe. We also have these movement parameters, so each void is moving at sort of a certain speed with a certain force and an initial speed range. You have this flocking behavior parameter, so you have alignment, separation, and cohesion. So that's sort of managing the flock behavior. I don't know how these map to individual voids. Maybe it just maps to the whole flock or the whole flock of voids, which is an artifact of the simulation. That's not necessarily mapping to a real bird flock. Then you have perception ranges, alignment range, separation range, and cohesion range again, ways you can control the flock. But is this something that we observe in real bird flocks, is the question. You have aging, which means these birds will, or these voids will have a certain lifespan, so they die off at a certain point where they're born. And ostensibly, they have some memory of what they're doing. That's an interesting question. You could have like a developmental boids where you have like young birds and older birds, and they acquire things throughout their life, and then if they die off, you get younger birds, and they don't have the skills that older boids have. I keep interchanging boids and birds, but you get my point. It would be interesting to see. But this doesn't really offer that. It just offers a lifespan here. And then genetic signaling. So this is where you have, I guess they interchange like a genetic algorithm or something with sensory signaling, which is interesting. Then you have visual performance. I don't think there's a paper attached to this. This is just kind of a simulation. And it actually shows like you can have different presets, so you can have different parameter values for these different, like you have calm, chaotic, swarm, signal heavy, minimal. I can reset it here, so I might want chaotic instead of swarm, and it gives me a different set of parameter values. Well, in any case, that's from Attention Mech, and that is on GitHub under genetic boids. So check that out if you're interested. And then finally, I wanted to draw your attention to something that I've been doing last week or so, maybe 2 weeks, is that I've been getting into Notebook LM, which is it's a platform from Google you can use to build customized large language models or train language models with input data and then produce not just a text summary, but you can also produce these sort of summary, it's like a summary where they simulate two people talking in like a podcast form, and they kind of it takes the input data and it produces this conversation. So this is something I did for our meeting archives, but also I did it for the Saturday morning NeuroSim meetings. I did this for the cybernetics meetings, and then I did this for the papers that we published from 2020 to 2024. So, this has gotten a good number of views already. I mean, good number for like what it is. And, this is the Netbook LM, which is Google, and they use Gemini. So this uses Gemini to digest like PDFs or YouTube links, and it produces this output. So it's for the meeting recaps, I gave it 6 months of YouTube data. So 6 months of meetings from YouTube. It just kind of went through that, and it produces about 20 minutes or 25 minutes of commentary. For the cybernetics meetings, which are like over 2 years, but fewer meetings, I think overall, it produced about 18 minutes of summary. And, the papers actually produced 22 minutes of summary. So it's really interesting because it sorts things out in a way that's you wouldn't necessarily think of on your own, but it also kind of puts it in a conversational framework. And so you can get this sort of, and sometimes it's not correct, or it's kind of near correct, but it's not really correct. But I think it's an interesting exercise. Yeah, so Jesse says, I saw the cybernetics one, listened a bit. It's interesting what the large language models actually pick up or not. Yeah, it is interesting that they'll, I guess, pick up on a theme and run with it. So I didn't actually go through the whole cybernetics one. The meeting ones were interesting because it kind of hits, the different kind of emphases that we're putting on different things over 6 month periods. So in one 6 month period, we might focus on we've been focusing, I think in this, for the last 6 months of 2025, we've been focusing on, large language models and reasoning and things like that. I think in 2024, we had more of an emphasis on, well, we've always had this sort of neuroimaging undercurrent, but we talked about all sorts of different things. We talked more about like AI ethics and embodiment. I mean, we talked about embodiment in the first half of 2025, but it's interesting, kind of those shifts in topics, but also, yeah, what the large language model can pick up. So it might pick up on a relatively obscure concept, or it might pick up on the main concepts over all of that content. So it also produces mind maps, which I didn't put out. I don't have them open, but the mind maps are just simply like kind of a classification of everything. So it'll have these subheadings and then sub-subheadings and so forth, which actually is really good for organizing the content over like a certain period of time. And that's one of the things we really struggled with in the group is like, we have these meetings and we talk about things all the time, and it's just kind of like things get buried and we forget about things, and it'd be nice to have a way to know what we're doing over a certain time interval and pull those themes out. So we do have that. So we have a number of tools at our disposal here. I've been trying to work on this because I noticed, of course, exactly that we have this lack of synthesis. Yeah, the mind map feature. So we have this lack of synthesis, and it's like, what I want to do is I want to make sure that we can go over sort of a larger time interval and pull out some of the themes that we talk about and do things with that. So, we have these AI summaries. I'm going to be continuing to kind of go through our archives, posting things, the summaries on YouTube, and those will be good. You can just listen to those. They're just audio files, but I've turned them into videos. Then we also have, I usually create a transcript of each meeting using a large language model, a different large language model. And those are like text summaries of the meeting. So like it has timestamps, and then it says, kind of what's been said. So we have like the meeting level granularity. We have the large kind of overview, the 6-month overview granularity. And then, so I hope with these kind of ways that we're applying large language models that we can get something out of this. And, so we'll come back to this. Yeah.
No, I'm actually really interested in that for a number of reasons. One, it's sort of like adjacent to Frontier Map.
Yeah.
In Frontier Map, it's much more trajectory oriented, but for people like it's also not really about kind of like documentation. But I've been thinking about this too, and I'm in like between being here and also being in, Ecolopto recently, and some other groups that are doing. I think there's a tool to be made here, or at least a procedure, like a recommended pattern, for people doing, like especially for interdisciplinary work, synthetic work, and there's like real ties to meta science, like what are I don't even know what related tools exist in meta science, but I'd be very interested in basically making one or trying to do such a thing, like do, well, again, I don't know if it'd be an app or an AI or whatever, or at least a procedure, like a methodology to approach to doing the things, because I think what you pointed out was like extremely important and relevant to this lab, but also people in the meta science community, people in the progress. Like I've been looking at like the progress studies stuff and Roots of Progress Institute, Cosmos Institute, which is like AI philosophy stuff. I've been all those things I've been busy with them this week. But at the level, and like this is the thing, like I'm particularly interested in, and I'm leaning heavily into this space of speaking, consulting, doing things in and around building the stuff. So I'm very interested, like it's I find it to be such an interesting um, lens to 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 um, to juxtapose the theoretical spaces that are being explored, sort of, I don't want to say de facto, but like in and of themselves, the spaces. And then there's the trajectory element, kind of the frontier mappy stuff. And there's like the individual map, like the individuals of the team that you're on that's building or exploring the stuff. It could be journal club, it could be this lab, it could be a working group, it can be your team that is trying to educate itself as it's learning the technologies, the products you're trying to make, whatever it is. Like what is happening in that space is, they're all different formats of like map versus territory type problems. They're all different formats of trying to document them. And so I am glad to see you experimenting with this and the tools that are available, but also I feel like there's an interesting and unique set of challenges that spark my interest for the people. Frontier map is basically existing historical contexts and potential future trajectories at kind of macro levels. Like you wouldn't Frontier map can inform what a team would be doing to explore space, but to explore the space and keep track of all the things we just mentioned from the different groups and the themes, and you have intra meeting and then inter meeting across the meetings, like trans meeting, the spans, and then the tendencies, and like, oh, here's the path that we didn't go down. I think that would be fascinating too, and I think we can do that now. Like I think that is literally, that's the best part of this. As a side comment, I was once again exposed to the debate of LLMs are or are not the future to AGI. But what I do think LLMs are great for is what we're talking about here, like these big time language processing models that can offer context, and then the little things that nice little add-ons like the maps, or the giving kind of sequences of almost like the not bibliometrics maybe, but like how, like the Google, when you search, how the usage of the term across time, is it more or less used, or you're more or less talking about Maturana, like the cybernetics video says, I think it says very awkwardly the name of Maturana.
Yeah.
He called him like Martin.
Yeah.
Like who? So I think he was explicitly referencing Maturana in the first few minutes,
Yeah.
and his take on an observer or an actor or whatever. But we haven't said the word Maturana in the meetings I've been in for several months, maybe close to a year at this point.
Right.
So it's interesting to kind of see who and what and where things go. So yeah, I'm super interested in making something there, and I don't, maybe we can talk about that more later at some point or something. But I think it's a good thing to be doing.
Yeah. Thanks for the feedback. So this is a playlist. It's called AI Summaries. So if you go to the YouTube channel and you go to the AI Summaries playlist, this will be getting populated over time. So I've just started with I think 5 of them, but yeah, I think we'll try to maybe try to evaluate it and see what the meta themes are, if there's something that's interesting. I know with the cybernetics meetings, it's been like this exercise in what do we want to do with it. We kind of reviewed a book, and then we went through some papers, and then it's like we kind of have done a variety of things in those meetings, and they're all kind of focused around different topics in cybernetics. But what is it that
Right.
we're doing with those meetings? We're just shooting the breeze and then forgetting about it, and there's there are themes in there that are, we can go and directly address them and say, oh yeah, we should talk more about that, or maybe that's a paper or something like that.
Yeah, and I know we kind of dubbed off into sort of the physical memory space, which is a very interesting space to be in, and we keeps coming up even in other circles. Um, and I know I've seen Amanda around. I don't know if she's going to want to start that back up again or not. But it is certainly good to I don't want to say document, but some kind of make some make make something of it, and in a non-combative way. It's good to make something of it, and make some kind of, even if it's just a general article reference point that's a little bit more accessible, and that's as kind of a disclosure for those who aren't um, savvy to the past here. I spent previously a lot of time documenting things in like Notion, and we've done various things of Notion, or like I think Bradley still maintains GitHub and all these other things, and it's good to do. But having things that are, I think we're in an era where the magic of what we can do right now is sort of I call it almost like the making everything have a much easier user interface. It isn't to be a GUI, but everything. The point, it's not like what Bradley is doing with the cybernetics meeting isn't a user interface per se, but it's taking this stuff that's kind of abstracted out or non-interfaceable and making it more. You're putting something to it that you can, now you can scroll on the timeline of a YouTube video to hear different parts of a discussion that have taken place over months, and that's the accuracy of it is what it is, but the sort of rough, you know, relation of the map to to the interface is much more accessible, and I think that's what we're doing on many fronts right now, and I think it's really appealing and fun, but also like we're learning how to both do that and to process it individually. And I think there's a lot like I I wish I had a little better connection to some people in the meta science tools space right now, because I'm really curious what they're dealing with in terms of these language models and the tools and the ease of creating certain interfaces right now to bring to light a little bit of clarity around the path that has been traversed, because you and I know the path, but the act of communicating what that has been to other people and making it something they can interface with is new and exciting and challenging, but also really good if it can happen in a decent form.
Yeah. So that's, I don't know, Jesse, if you had, I know you said yesterday at the open source meeting that you had something you wanted to talk about at this meeting. You kind of were saving up some of the more sort of the meatier stuff for this meeting. But I wanted to first ask maybe Vidhi or Morgan if they had any other thoughts about the stuff that I presented.
Well, I'd love to say more about the C. elegans simulations, but I'm still waiting to get more info about the. Anyway, I was just going to bring up the large language model diplomacy match. if you're gonna be talking about LLMs, did you see that?
Which one was that?
This is where they had, kind of before big models all play diplomacy against each other.
Oh, yeah, I did see that, yeah.
Okay. I mean, not a fully serious thing, but
yeah.
I just thought that was so hysterical.
Yeah, I think that was I think you put that in the Slack. It's like where, I guess, DeepSeek became a tyrant and like different models took on different personalities or something.
Yeah, well, we gave them personality
Yeah,
types.
yeah,
Like, yes, yeah.
But it is like expressing it.
So, I'm on the bus right now, so
Okay, yeah.
I'll be able to say more in just a bit.
All right, yeah. That's it. We talked about a paper like similar to that, probably last year. I don't know. It was like we're
It's definitely they're not the first to do diplomacy. Yeah, yeah. It got at the whole, because diplomacy seems like such a human game in terms of the alliance formations and things like that. How yeah. So in the original one, they played with humans. If you know,
right.
Yeah.
Okay, yeah. And then Vidhi said, not really any thoughts just listening, but I really like the new playlist and would want to see more. Okay, yeah. Coming soon, I guess. So yeah, Jesse, why don't you discuss? You wanted to talk about some of the good things you've been doing.
Oh, I think the easiest and most there's just been so much this week, and that's I guess a good thing. But it's just I realized I think last night I realized like my voice is just tired from talking so much this week, and like my throat was like I didn't know if I was sick, but I was just like, oh, I need to rest my voice. So I will. It's good news for everybody here. I'll probably be somewhat restrained in my speaking today, but I'll share. I'm gonna take the easy route and just share. I'm just gonna share some things on that I posted on LinkedIn because that's the easiest way to do it. And my main thing is gonna be talking about the um, oh yeah, I'll mention plot twisters too. But yeah, we had it for a really brief thing. There's a busy day at Ecolafto. That was that yesterday. No, that was Thursday, and there was a session with Peter Voss and William Edward Hahn on principles of AGI. The second one was with Paul Hahn. We're going to talk about that one if Morgan wants to say things later. To know, and it's also fun because Paul is literally a builder and thing, and there's a lot of really cool stuff happening in this space here. Peter Voss and William Edward Hahn. I haven't seen any great links for it, but machine perception, cognitive robotics. So cool stuff. And then Peter Voss interested in human level, cognitive AI. And I don't know if there's a good image here that I can show, but basically cognitive AI, and he's of the opinion with Jan LeCun that LLMs are a dead end for AGI type stuff. He's a very positive view on AGI in the sense of, it will improve the world and good things like that. Looking for engineers, 5 months ago, maybe not. But Peter Voss is a very interesting guy. He's got a lot of opinions. Very interesting take. One of his interesting takes was basically, I documented some things there. Yeah. So there was an interesting discussion here, which I'll really quickly go through this. But there's just some notes from the talk with Voss and Hahn and others. But basically, there was an interesting side. I wish we talked a little bit more about it, but there's an interesting sidebar about dev AI and developmental AI. So of course I plugged us, and I plugged Josh Tenenbaum, who does a lot in the computational cognitive science developmental space, and others at MIT. it would have been fun to summon both sort of our talks there and sort of the Josh Tenenbaum agent to the conversation. Voss has an interesting differentiation between consciousness and self-awareness. And I think it was quite interesting because it is the case that there's a lot of consciousness is sort of a very murky philosophical thing, a bit like defining intelligence. You know, you can kind of get into the space of definitions and whatever. Self-awareness is I think he's demarcated it relative to the general consciousness thing. So like, is something self-aware or not? And so on. Let's see. So Voss made there was a lot of interesting talk about, you know, can a model be updated in real time? And if not, it's an inherent limitation if it cannot be like biological intelligence or things that we have to, you know, deal with. Whereas like, you know, he was saying like, oh, cognitive AI, what he's calling that, you know, would be more adaptable and flexible that way. And I'm trying to see if there's anything down here that says what cognitive AI is to him. Maybe you know, Bradley, can say it very well. I know what it is, but it's not coming to my mind clearly right now. One of the other interesting points was also, if there's no common data representation, then they have disadvantages of both systems. And I wish I wrote down which systems that was in reference to. I think it might have actually been a reference to the Daniel Kahneman system 1, system 2, as opposed to just LLMs or hybrid things in general. The LeCun stuff. There was an interesting also discussion point that we've talked about here many times. And I think I even wrote this in our Slack, but basically saying, I remember being at an event like 4 or 5 years ago and having the same conversation about how, you know, funding and deep learning and the economic incentive to be deep learning oriented just tilts so much emphasis around it. So even with people like John LeCun saying, you know, we need to do some different things, X, Y, Z, there's you know, the markets and the push and the data and people that have the data. There's a lot of reasons for why deep learning is what it is. As a reminder for later, if I can remember this or someone can remind me, there was a post by the head of like model and behavior policy at OpenAI that I saw earlier, and maybe it will be good to touch upon too. But other topics: intelligence versus far transfer, analysis and extraction. I tagged Johan, Dr. Johan John, who I kind of wish was in that conversation, because he's done so much good writing and discussion in that space. Cognitive light cones from Levin, fast slow, meta brains from us, generalizations versus instances that bring about the generalization. These are all kind of things as Voss is discussing, like components of AGI, I guess. Whenever I mention Daniel Fagella, I feel like you know, I'm sure Daniel would disagree strongly with Peter Voss's views of the future. And what I like about Dan is that Dan is doing a very, very, very good job of demarcating a specific trajectory. And whether or not I agree with all aspects of what he's saying is what it is. But much more, I think it's so important. And I wrote this somewhere, but it's so important at this time where the future is so uncertain, is to find people that are, regardless of whether or not you agree with them, but like find people that are delineating, if things do go in this direction, here's where it can go. And what does that look like? And how do we navigate relative to that? Because I find that to be, there's so much sort of weird bickering about what to do and the squabbling parts of it. It's like that's nice, but like we really need to steel man the roots that are going to go there and make them as clear as possible. So if we know if we are traveling down that road, let's know what the on ramps and the on ramps and what all these other things are going on going to be. That's my take on it anyway. But yeah, the Diamond Age, all these great, interesting. It was interesting, slightly future discussion, a lot of allusions to it, and then yeah, excuse me. Oh, this one's good too. A lot of this is kind of, this seems to be out of order some, but whatever. The Systems 1, Systems 2 stuff was there. There was a really fun session, which I wish we spent a little more time on, the ready at hand transparency stuff. I mentioned that. I eventually got to calling it to Heidegger's stuff. The Voss is very interested in this Helen Hawking theory of AGI, which he talks about here, and I'm not going to get into it right now, but he has his own particular view of what it's going to be, and this is a nice post for it, just to show it here. I thought there was another image that would explain some things, but yeah, and yeah. So that's pretty much. It was a very wide-ranging conversation. It was very fun, and it was sort of interesting to have this juxtaposed directly to this one, because you had like big theoretical macro, and then how do we build skin that's human like a couple hours apart. So that was fun. That was Thursday. There's a few. I'll talk a little more about the Cosmos event also, which is sort of the main thing I'm getting to. But before that, any questions or comments on this stuff? I've got that ready.
No, but I'm glad you had like a good, like, summarize that. It's always good to see like how people are thinking about theory versus putting things into practice, and then how you mentioned at the open source meeting yesterday about like, or we had this discussion about like how there are these debates, or how we have like these kind of discussions in the literature, like, we could talk about the AI literature as an example, where people will frame things as debates, or they'll frame things as sort of like their pet theory, or they'll frame things as like something that's maybe not so controversial as being this great controversy. And then like that's how like the conversation proceeds. So the priorities are based on those kind of debates, or those those kind of frameworks, whether they're warranted or not. So it's like we could take like the AI debates that we had, what's his name had, Gary Marcus. And like it was like, okay, well, these are debates about, some of these distinctions of course are maybe semi-technical. So it's like you have neurosymbolic systems versus neurosystems versus symbolic systems, and like how do we think about it. And of course, maybe the correct answer is, of course, neurosymbolic systems are superior, but we'll frame this as like a debate so that we can say, well, this thing versus that thing, and kind of facilitate different arguments and things like that. But at the end of the day, there's no real controversy. It's just kind of like, we kind of know the answer, maybe, or maybe we kind of assume the answer. Maybe it's not the right answer, but and that's kind of why people do this in the first place. But I think a lot of times we use these things as mechanisms for like kind of getting at, or sometimes we use these mechanisms in a way that sort of assumes that we're going to get something out of them that we never get. Yes, I mean, like, I guess what I'm getting at here is that, we talked about that yesterday, and then I think there's this really interesting kind of follow-up to be had about like, how do we think about the way in which we discuss these things? How do we put this together as like, a set of debates, or like, what it is, what's the priority in a certain area?
Yeah, and what's actually, and I think this is something this is why I keep mentioning some of the meta science stuff. Like there's some really things from I was a part of the meta science conference, or I wasn't there. I listened to one of the recent conference, I don't know, discussions from. It was on somewhere online, and I was listening to that a while ago. But both meta science and progress studies and these, I think there is a lot there, and I think that's like a lot there in terms of how do we actually have functional discussion that evaluates pathways. I think that's really what it is. Is I as a side. Well, I mean, I guess this also happened this weekend. I haven't really I haven't really talked about it, and it's still in development, and I have to incorporate some of the edits that you've helped me with. But I don't know if this is where you're going with things or not. But I'm particularly interested in. I kind of want to make something that I'm going to call almost like destination-based research is my working title, and I have to make a like an OSF page around the project, and I'm about to do it. So it's like a soft tease here. But in this essay, which I did for, it basically was adjacent to the Roots of Progress blog fellowship thing. I decided to basically take this concept of longevity and say, hey, we need to do more than just biotech, basically, or at least thinking at the level of biotechnology is what it is. And I'm not going to go through this whole essay right now. I don't have the stamina for that today. But what I will mention is sort of, I've used this term destination discernment, and I even spell it correctly in the essay too. But basically, the ability to chart meaningful trajectories through complexity, and in this case, the development, care, and innovation through social, institutional, technological complexity, leading sight of what matters. Okay, that's pretty. That sounds pretty hand waving to just dive into it, that definition. But where I'm going with this is like, I'm trying to take the longevity debate, the longevity arena, and turn its focus a little bit onto these, essentially what we talked about here. Like I talked about mentorship and like the infrastructure of making these changes, and then I get into some specifics about leading without burning out, cognitive longevity, all this stuff. How do we have more functional interactions on these kind of things? So I'll leave it at that. You can read it there if you want to, and I'm going to be discussing this more later. But well, for destination discernment as a thing, and generally getting at these, like kind of what I was saying before about the recapping the meetings, like how do we demarcate this stuff, and then specifically, how do we actually have really good discussions that describe where things are going? And I think I do give I do try to give credit to Dan Fagella for inspiring that view some, because he had a really nice presentation that I was able to attend, I think last year. Also, Dan Elton was there, so shout out to Dan Elton. I miss him. I think he's going to come back to Boston, so hopefully be back here in Boston with us soon. But anyway, like, how do we actually have more functional discussions? And yes, also the synthetic stuff we talked about. We've had this sort of recurring theme here about, not just having discussions, but putting some time into the synthetic part of it. So yeah, to any I'm gonna make 2 quick shout outs, and I'm gonna say the Cosmos stuff, and then I'll move on. So anything before I do that?
No.
Okay. Shout out for Plot Twisters, because the Plot Twisters crew got this. There's folks that have done the fellowship. Jenny is sort of fearless leader, and then Amanda's a longtime person, and Joanna are all to this, and they've applied to this particular fellowship, and they got it. So we'll be working on this small hassles court. It's sort of a mini game in this thing, and it's, you can read the article and get into it, but it's sort of building out more of the actual land and sort of the functioning and the ways of things that are going to happen in the Twisterland game itself. So check out this post for more. But congratulations to them, and looking forward to hopefully furthering that this summer. And then really quickly before I forget, this post, I'm not even going to talk about it. I'm just going to mention it. Maybe if we have time later, I'll come back to it. But this post about, Sam Altman was like, yeah, this is an important post. Joanne is the person running the I don't know, model and behavior. Yeah, lead model behavior at OpenAI. And what they're saying is we build model to serve people first, increasingly connect to the AI. We're prioritizing research on how this impacts their emotional well-being. So all the mental health, computer interfacing folks out there, maybe you're getting a little shine and more opportunities here. Obviously important in general, but yes. And then I pull these other quotes out saying this, 3 ways they're 3 questions they're looking at. Why people might attach emotionally, how we approach this question of AI consciousness, which is again that particular interesting C word, and then how that informs how we try to shape model behavior. In the coming months, we'll expand targeted evaluation of model behavior that we contribute to emotional impact, social research, and hear directly from all this stuff. And I'm just really curious both what they're going to do and like, I don't know, it's kind of funny because there's so much inertia about, like, I mean, just say just the word Cambridge Analytica. All right, that's something that we know is a major actual factor in presidential elections. That's sort of somewhat uncontroversial to say. And there's even more stuff there at the level of, stirring the pot emotional or social, emotionally, politically. And then, it's curious to see what OpenAI's public facing version of this is going to be versus what they do and what they, subcontract out to others, and in terms of their, are they going to try to basically become the Facebook Meta of, Facebook has all this personal data on interactions, but not interactions with necessarily an agent or an agentic AI, LLM, chat GPT like interaction. So we'll see. But as the saying goes, I told you that story to tell you this one. And so the actual main point of what I wanted to get to was this. This is a really, really, really fun event. I was lucky to get into it. For super quick background, I think I put the thing here. Ooh, I just did something weird. Sorry. For a quick background, I'm not going to go to this article, but there's a big Oxford seminar, AI philosophy. McCord's sort of the leader of the Cosmos Institute, and they've had a whole, different things for each week. I happened to be able to attend this one virtually. I wanted to do all of them, but there's just so many people, so many popular things going on. But I'm actually pretty glad I got into this for a few reasons, which I'll say later. Unbeknownst to me, I would find out later this week that Plot Twisters got a similar governance type thing going on too, so it may help with that. What they're doing and the fellowship is sort of tied to this too. But basically, the Habermas machine is sort of this. Is this going to be a good link for it? Are there any pictures here? It's sort of a way of generating some useful consensus. I'll read this. However, this can be a challenging when discussing the present very difficult opinions. Tessler and co. Investigate whether artificial intelligence, that's what AI stands for, can help groups reach a consensus during democratic debates. The authors trained large language models called Habermas machine to serve as an AI mediator that helped small UK groups find common ground while discussing divisive political issues such as Brexit and so on. Compared with human mediators, AI produced more palatable statements that generated wide agreement and left groups less divided. The AI statements were more clear, logical, and informative without alienating minority perspectives. The work carries policy implications for AI potential use to unify deeply divided groups. And sure, it was interesting to compare this to, and this is based off of Jürgen Habermas' theory of communicative action, and philosophy behind it is there. I'll come back to sort of the meat of that in a second, perhaps. But it's very interesting to compare this to this, which is I attended this in May, and this is sort of an MIT variant of a similar project. In it, they actually I won't go over this whole year, but they basically have these different modules that do different things, like Socratic dialogue, face of the crowd, dynamic deliberation, and these different I think this is a decent one to show. Oof, yeah. Like it was a totally separate project, by the way. They found I don't know why it's kind of annoying, but they found it's a depolarization effort what they found in their own work for the Socratic dialogue. Showing people the face of the crowd demonstrates how much we agree with each other. And model conversations increase nuanced discussion and the legitimacy of the platform. And I think what that means is like is this discussion itself viable, or like is it fake news? Is it just biased? Like it's saying it's making the discussion itself more legit. And then comment ordering, representation, legitimacy in the process, and sense of respect. So this is a really interesting comparison, and I'm gonna do more in the future, probably with data and direction, honestly, because this is a super great topic for them, which is the newer project I'm doing, and also interns and stuff. More about that later. But to compare this to what's happening here, this mediator stuff. Yeah, I like this summary, not just because I wrote it or whatever, but it's talking about it's not a decision maker but a mediator, and I think that was a very interesting approach to what's going on. Is like the Habermas machine talk, and even though it was done with a model, like much older models than are currently state of the art. I forget. I think it was some awkwardly named one that I can't remember right now. But the talk, and I don't think I say this here, what was really good about Chris Summerfield's talk was he had a very interesting point that I'll kind of center, and then maybe we can talk about it or move on to other things, because I know I've had the mic for a long time. But a lot of this discussion, this is mostly just other papers. Yeah, this is the point about kind of using an older model. And they're going to update that. Yeah. Oh, I didn't see this before. Oh, that's cool. Oh, it was 14 hours ago. That's why. Okay. Anyway, the point Chris made is sort of one to 2 points. One was differentiating AI and sort of psychology or the personhood of it, which is like very, everything's agentic AI right now, which has this sort of connotation of almost personhood to it. But differentiating the AI and psychology of AI from AI mechanisms or structures that afford or allow things to happen. Like, yes, this was an AI mediator, I guess, but it was more looking at what can AI do mechanistically in terms of how it's structuring a debate or discussion, which kind of ties into a little bit what we were talking about too. Like, not exactly what would a behavior must be for, synthesizing orthogonal lab meetings, notes, whatever, but this is how do we use AI to constructively and meaningfully in a legitimacy in a legitimacy building way actually have people feel like what they're doing is a meaningful discussion. Are you building on something? And so that was one of the points. Well, I guess that's both the points together, like both sort of the differentiation from AI as psychology or agential stuff in a it has to be about how like the mind or artificial mind works to AI as tools and means and infrastructure and mechanisms that facilitate the things that we want. So I think that was sort of a very interesting point that he made in the talk. It wasn't the central point of his talk. Most of his talk was basically going through basically this paper and other papers. I'm curious if there's any other good diagrams here, but yeah, he talked at length about the the data drivenness of what was going on and how AI helped good things happen basically. So yeah. There was something else I was going to say, but I think I'll leave it at that for any questions or comments, because there's a lot of good things there, and I do look forward to basically doing a deeper dive and comparing it to some of the Gov Labs work from the Alicea group.
Yeah, so Echolopto seems to be doing events with a couple members of our neurotech floor here. So Yo-Yo had one last weekend, and Paul Hahn was the ESKIN, and he went through a bit of a review on material properties, manufacturers of products that perhaps used with prosthetics, things like that. And definitely some a little, and some coverage of just the issues that you have with bioelectronics, and in particular the issue around MEAs and how you need to choose a different material for a successful um, MEA device other than what we use for kind of traditional, say, electrodes, certainly non-invasive electrodes, because neurons just won't grow on silver, as he points out. So some good stuff there, as it relates to the more, I think one of the things about eSkin that has people most interested is, of course, giving people a sense of touch, and in particular, the sense of touch with the sensitivity that you have in your fingertips. For instance, would be awesome, but is particularly difficult. Yeah. So just nice to see people that are working here are getting there. Out. I do you know the Echolopto organizer, Jess? I'm just wondering. I don't know.
You mean Abby, or what do you mean?
Well, just I haven't actually talked to Yo-Yo or Paul about, like, did he reach out to them, or did they reach out, to yeah, just not sure how they they both ended up in the same week. Like I don't think they know, like I don't think they know each other here. Yo-Yo's a student at Minerva,
Right.
and Paul, Paul still kind of works from his own space, even though he's a member here at the tower.
Yeah, I don't know how the connection was formed, but I mean, you could probably ask Addy about that.
Yeah,
but there's, he's trying to get together a lot of bringing people, especially in sort of the sensing and new senses kind of spaces. He's trying to do stuff there, so that's probably how they found each other.
Yeah,
or he found them, I guess.
Yeah. No, it's cool. It's also funny to bring up Cambridge Analytica, since I've now met Alexander Kogan. Seemed to be he's not a member here, or at least I don't think he is yet. But he's a member of the last kind of working space. It was that was a funny conversation. I didn't really know what to say to him. But we had this isn't totally related, but just one of the updates I have is having some meetings with Katerina Wojtek, the now postdoc at UC Santa Cruz, working on organoid culture, and hoping to have her come speak like mid or end of July. So really excited to learn more about what she's trying to commercialize, as well as just she seems open to helping us in our nascent efforts to get a dedicated organoid culture facility going here. So that's awesome.
Great. That sounds great. Yeah, thank you, Jesse, for the conversation about this. And yeah, it looks really interesting. So Morgan, did you want to talk about did you want to say anything else, or do you have more time to?
So this week is Edge Esmeralda. It's one of these pop-up villages, and just hoping. One, I'm going because there's a planned Neurotech summit that is that's being organized by Patrick Minot and Sean Escola. So, a good opportunity to talk with neuro AI people. There's also going to be some an opportunity to pitch projects for. They're offering up to $500,000 to support what we hope is community lab around these kinds of neuro AI projects. And yeah, so working with some people, including Elliot here at Biopunk and Sam at Metamorph Labs to work on a pitch hopefully for Monday.
Okay.
And that's Then there's a neural interface meeting the week after, and then I'll be up to the Allen Institute for open science and undergraduate education, kind of an educator's workshop.
Yeah.
So looking forward to that.
That's great. Yeah. Okay, yeah, let's move on to this paper. This was something I think Vidhi shared in the Slack as well. So this is from the arXiv. This is a survey on compositional learning of AI models, theoretical and experimental practices. The authors are from Michigan State Department of Computer Science. So this talks about compositional learning, and we talked about that in the previous meeting. It could have been last week or the week before, where we talked about compositional or what compositional learning or what compositionality is, both in I guess in three aspects: in linguistics, in AI, and then in like behavior. So we had in cognitive science more broadly than linguistics, just in linguistics, which was actually a pretty technical definition. And then, of course, in AI, where you're trying to assemble things, things like, different parts of a program in a neural network. So they're going to talk in this article about compositional learning, kind of going over thinking about reasoning in an intelligent agent. So they actually going to talk about this. Researchers have examined this phenomenon from cognitive, linguistic, and psychological perspectives. So they have these references here to talk about sort of the diversity of the definition. The abstract reads, compositional learning, mastering the ability to combine basic concepts and construct more intricate ones, is crucial for human cognition, especially in human language comprehension and visual perceptions. We talked about in linguistics, it's about language comprehension, and then, of course, there are these visual primitives that get put together for visual perception, and there are other aspects of cognition that involve compositionality as well. So you can see where you want to be able to simulate this ability to build upon artificial models. This notion is tightly connected to generalization over unobserved situations. So the ability to generalize is, especially things you haven't seen before, is tied to sort of the compositionality. So if you can put things together in pieces, you can say this thing is related to this thing, or you could scaffold upon previous things that you've learned, you can generalize to things that you've not seen before. Despite its integral role in intelligence, there is a lack of systematic theoretical and experimental research methodologies, making it difficult to analyze the compositional learning abilities of computational models. So, this is something that if you're simulating an intelligent system or you have an intelligent agent and you want to figure out how it's learning things compositionally, it's hard to really know how to go back and trace it out. And we talked about some of the tracing tools that exist for AI models, where you can trace out things in a neural network. We talked about that last week. So those are just one set of tools, possible tools that we might use. In this paper, we surveyed the literature on compositional learning in AI models and the connections made to cognitive studies. We identify abstract concepts of compositionality in cognitive and linguistic studies and connect these to the computational challenges faced by language and vision models in compositional reasoning. We overview the formal definitions, tasks, evaluation benchmarks, variety of computational models, and theoretical findings. We cover modern studies on large language models, provide a deeper understanding of the cutting-edge compositional capabilities exhibited by state-of-the-art AI models, and pinpoint important directions for future research. This introduction, I just mentioned that, this is a diverse kind of topic. You have many different fields that have kind of approached compositionality in different ways. One way that they define compositional learning is, they say here, the compositional learning and reasoning of an intelligent agent refers to the ability to understand and manipulate complex structures by decomposing them into simpler parts and then composing those parts to form new complex concepts with a coherent understanding. So the way they're kind of thinking about compositionality here is that you have this complex structure that maybe emerges, and then the agent can take that complex structure, decompose it into simpler parts, and then recombine them in different ways. And you can actually then get these new emergent features that give you a coherent understanding. And so this is something, of course, again, that relates to generalizability. In other words, if you learn something, you can generalize that skill to other areas. You can transfer that training to other areas. Sometimes you've not observed those things, but you can actually leverage what you've learned before to help you in that situation. Now they have this formal notion of compositionality down here. Okay, so this originated in natural language and semantics research. And of course, we talked about some of the theories there that elaborate on this concept. So their principle of compositionality, and this again comes from natural language and semantics research, it's defined as the meaning of a whole is a function of the meanings of the parts and of the way they are syntactically combined. So this is again very specific to language, is that you have parts that they're combined syntactically in certain ways, and then those provide meaning. So you might have, like, for example, different word structures or different, different parts of speech, things like that, that get put together maybe into a sentence. And so syntactic means that it's syntax and how those are combined. And then this provides the basis for the meaning of a whole. So the meaning emerges from the way different things are combined and built upon. So there are actually, this is one way to do this, and there are three methods of getting here. So you have new meanings, new basic parts, new constructions. So you can have So, for example, you can learn new words. You can learn variants of words. You can construct those new words into new sentences that you've never seen before. And then they can have new meanings, both new constructions and old constructions, new and old types of sentences. Maybe you've seen them before, maybe you haven't. Acquire new meanings. So you could think about this in terms of memes. I think I talked about that last week with memes, where you have, an image that's like maybe a photograph from some context, some semi-famous photograph, or some drawing, maybe a cartoon, and then it'll have like this meaning, original meaning, and then you take that and you use it as a response to something in the world. So this thing, it doesn't necessarily acquire, it does acquire new meanings, but the original intent is sort of thrust into these new contexts. So the new basic parts of the meme are kind of like, you maybe get a new image. Maybe it's the Sickos meme where you have this cartoon of this creepy looking guy looking through a pane glass window and saying, yes, yes, mocking someone's suffering. And then you might post that into as a response to someone you dislike getting their comeuppance. Or you might post it as a way to sort of, express your some sort of ironic detachment or something like that. So there are all sorts of new ways you can build memes, new basic parts, new constructions, and new meanings, that it'll take on new meanings as you apply it to the world. Okay. One of the earliest formalizations of compositionality was grounded in grammar trees, when cognitive science proposed an information processing approach to create a model of the mind. So this goes back to, I guess, early cognitive science, where part of that cognitive science hexagon is linguistics, and building models of language, and then linking that to cognition. And cognition, of course, is information processing in the brain, or of the mind. And so you're creating this model of the mind where you build this grammar tree and you say, this is how, the mind processes, or the brain processes, this cognitive stuff. So, there are all sorts of computational models in cognitive science. You have things like grammar trees, which grow directly out of linguistics. You have connectionist models, which kind of grew indirectly out of a lot of the ideas about how the brain worked. You have some other you have cognitive models. So these are where you have these boxes and arrows models that show like different cognitive functions that are connected to other cognitive functions, or maybe parts of the brain connected to other parts of the brain, where you hypothesize about what that part of the brain does, and then you put that together into a systems model. And so, you have these different models of the mind that, the key thing that links all those models together, that the brain and the mind is doing information processing, that it's doing it kind of like a von Neumann computer, where it's, doing these discrete operations, it's operating from some code or some instructions, and that this is operating in a way that we can, that's a systematic way that we can analyze. So, this is really kind of, sort of goes back to the birth of modern cognitive science, and it grows out of linguistics. And, linguistic constructs provide good examples and good lessons about what compositionality is and its capacity. So compositional understanding of linguistic constructs has multiple aspects. So, for example, a nesting description such as the black tall woman on the left of the car conveys the intersection of multiple adjectives and spatial relations. So much like the meme, you have each part of the image is a meaning. their spatial relations. You can map that to language. In this case, we're talking about a sentence, so it's a description, and you can map that to a visual image. And that's, there's this sort of aspect that involves information processing. So the composition is defined as the intersection of multiple concepts. However, there are cases in which the direct intersection is not applicable, and the meaning should be inferred from the concepts in the global context, such as recognizing the sentiment of the following sentence. The pizza is so good, I hate this place. And so that's, obviously, if you took that literally, that would be an oxymoron, but it's actually that I hate this place is sort of means I don't hate this place, I love this place, but I'm just kind of not happy about it, or something like that. So there's a sentiment buried in here that's not obvious. Say maybe if you don't have the context, right? If you don't know that you're using hate as like a term that's like, I actually love it, but I in spite of myself, basically. So this is, what compositionality is and what it can allow. And of course, this has a linkage to large language models where you can say, there's a model that's learning this language. It's naive to the language as a speaker, so it has to learn not only the syntax, but also the way in which it's constructed and the meaning. And so the thing about like humans is that we learn a language as a first language. We grow up in this sort of milieu of the language, so we never really think about having to learn it. And maybe if we learn a second language or a third language, we have to learn the context. And, if you learn your language directly from Duolingo, you don't necessarily get that context. So when you actually go to a place where they speak that language, it's a little confusing because you don't know the context that native speakers have. And so it's hard to do. And then imagine if you're a computational model on top of that, where you're very naive to natural language and you don't have necessarily, you have access to the visuals, maybe not. And so that makes it harder still. Despite natural language being a prominent manifestation of compositionality, this can be expanded to other areas of human intelligence, such as vision. The same notion of intersection, as well as part-whole compositions, is essential for visual intelligence. And so compositional learning is important in complex tasks where high-level goals must be decomposed into smaller sub-goals and plans. For example, when instructing an agent to navigate from one point to another. From the computational modeling perspective, traditionally formal grammars have been the means to address the compositional understanding of various modalities, which maybe are, rooted in language but extended to vision. While these models inherently address computational structures, using them alone, that is parsing raw and noisy data into a structure with manually designed grammars, will be brittle in real-world situations. So this is an interesting passage here. So you can have a model that addresses compositional structures where you're parsing data into some sort of artificial grammar. It's contrived, and because of that, it's brittle in these real-world situations because it hasn't acquired the context and it hasn't had the experience of the language, whatever that means. So it's a really interesting implication for large language models where, how do you provide that experience? Is it just mainly working with the language over and over again, or is there something else there? And so they're actually in this paper, they talk about data-driven approaches, but also combining that with neurosymbolic techniques. Okay. And then they talk about several studies providing much experimental and theoretical analysis, indicating the competitiveness of these models in expressing compositional structures such as context-free grammars. Their expressive power added to the robustness in dealing with noisy data, makes the neural technique applicable to realistic situations. So they're talking about using kind of a neural network approach in here somewhere. So that's what they're saying, is that there's this expressive power and robustness to dealing with noisy data, and that makes those. So yeah, they talk about that up here. They talk about neurosymbolic techniques versus data-driven approaches based on artificial neural networks. And so this approach, this former approach here, is what they're referring to down here. So there's this expressive power of data-driven approaches, and they can express these computational structures such as context-free grammars. And I guess they're maybe arguing that neurosymbolic techniques don't have that ability, but I'm not really sure. In this paper, we examine multiple aspects of compositional learning, including cognitive aspects, computational models, and evaluation paradigms. So if we go down to this figure here, this is the outline of covered concepts. So they actually kind of talk about important data sets. So there's this one set of data sets, systematicity or novel composition. There's this data set called CRAPE, which is compositional representation evaluation benchmark. There's SCAN, which is a simplified version of the ComAI navigation tasks. There's GSCAN, which is where your grounded version of SCAN. So this one up here, the ComAI navigation tasks, are where you have this data set that evaluates the model's compositional generalization across primitive commands, where you have these sort of, the model has this experience with both the primitives and similar compound structures. And then they test for unseen compounds. GSCAN is where you have this grounded version of SCAN. So it's where I guess you have these splits of the data set, and they focus on some form of novel composition of known concepts. Then there's PCFG set, which is probabilistic context-free grammar string edit task, and COGS, which is compositional generalization challenge. Okay, then there's the set of productivity or linked generalization data sets. Of course, CRAPE is involved in also under that category. PCFG set is also under that category. Then there's another data set called CFQ, which is the compositional freebase questions data set. And then the COGS data set. And so they give some interesting information about generalization criterion. And so they have a couple of tests. This is from the PCFG set data set for the benchmark. They have this concept called substitutivity or synonymity test. This uses an input sequence with an atomic unit replaced by a synonymous atomic unit to evaluate how the model prediction changes. So you have these different primitives and you replace it with another primitive to see if it changes the model's prediction. Localism is tested by using input sequences composed of smaller sequences A and B. The model was used to translate the full sequences first and then forced to process A and B separately. This evaluates how models deal with local versus global concepts and how that contributes to compositional reasoning. Then overgeneralization is a test that evaluates the model's results on input sequences that do not conform to the general rules of the data set. So input sequences that are exceptions to the data set rules enable us to look at overgeneralization and some of these other types of exceptions. So the discussion in future directions, there's been a large amount of research on the compositional learning ability of humans from a cognitive perspective. However, from the AI machine learning perspective, ideas are borrowed from both cognitive and linguistics, and compositional tasks and models are design focusing on narrow aspects of compositionality. So their investigation of AI models indicates several challenges regarding the design tasks, benchmarks, and theoretical frameworks. So this is the first one is synthetic and unrealistic evaluations. So one issue in current evaluations is that controlled and clean tests of compositionality are mostly synthesized. So these are where you don't really have really realistic data. It's just something that's been created for the purposes of the benchmark. So synthesized questions are used to query knowledge graphs. However, more recent studies on language models evaluations of compositionality focus on more challenging problems, such as multi-hop question answering and complex puzzles. Another issue, and this applies to mostly to large language models, is data contamination, meaning that you have issues with the realistic nature of a data set, but also, when you train a model, it will see some of these things that you're trying to test for. So if you're looking for compositionality, the training set of the large language model is going to involve some of these compositional, compositional components in the flesh, so to speak. So it recognizes those things from its training. Now, whether that's contamination or whether that's how we actually do composition, it's hard to say. But it'd be nice to have, a system where we can pull apart the effects and the causes of composition. Then, in a lot of studies, we have this inconsistent theoretical methodology. So, understanding between methods, like between transformers and neural networks and other types of models. How does composition happen there? What are the tests being applied, etc. And then there's this cognitive motivation. So the fundamental capabilities of current AI models have been debated and criticized by scientists in cognitive science and psychology. Despite giant leaps of performance, progress in modern AI, there are distinct differences between these machines and human intelligence. Evaluating different models reveals that they often rely on simple pattern recognition instead of a holistic understanding of a problem grounded in reality and situation. Understanding human intelligence from cognitive science literature suggests that we must move beyond current engineering trends to build causal models of the world that support knowledge and understanding. The key ingredients of such human-like rich and efficient learning are compositionality and learning to learn, and that's reference 60. So that is this paper. I think it's interesting. It kind of gets in the weeds of some of these methods, and I'm not familiar with a lot of the methods, but I think it's an interesting kind of follow-up to the compositionality stuff we talked about last time, and how maybe like a large language model can deal with this, but also how to think about this in terms of cognitive models, where we're trying to figure out how maybe like the mind deals with compositionality or clarifying that process, assuming that we actually do information processing. Okay. Are there any questions or comments about that paper?
No, just, yeah, it's a super important topic.
Yeah.
Don't, yeah.
All right.
Great survey.
So this is, I'm going to finish up with this paper here, and this kind of goes back to the thing we were talking about with genetic voids. So remember the genetic voids, we have these agents that you give them parameters to behave, conditions to behave under, and they behave in these collectives, and they form these patterns that are emergent patterns from their collective behavior, from their individual behaviors, and we find that fascinating, and it's also, adaptive and intelligent to some extent, and so that's really interesting to, it's just an interesting set of observations, and we can maybe analyze it. But there are things going on with the individual agents. And so this is a paper from PNAS Nexus, and this is collective decision making by embodied neural agents. Guillaume Dumas is on this paper. Marco Dorigo is on this paper.
Axel Cleeremans.
Yeah.
As well.
Yeah. So these are all people either doing AI or like swarm intelligence or other areas of this kind of
consciousness.
Yeah, consciousness.
Yeah.
Okay. So this is they're going to be talking about collective behavior and these embodied neural agents. So, our genetic voids are not embodied. I mean, they're point dots or points. And, there's no assumption of embodiment there. It's just kind of like there's this agent, it's this thing, this program that kind of interacts with things in the environment. But this is where we're assuming some sort of embodiment here. So the abstract reads, collective decision making using simple social interactions has been studied in many types of multi-agent systems, including robot swarms and human social networks. However, existing multi-agent studies have rarely modeled the neural dynamics that underlie sensory motor coordination in embodied biological agents. So, aside from the swarms, we're interested in these sort of embodied agents that exhibit sensory motor coordination. That is, given a stimulus, it produces a movement output or a motor output. Not quite like what we have with voids, but it's has this sort of feedback loop, this closed loop feedback that works from being in its environment. In this study, we investigated collective decisions that resulted from sensory motor coordination among agents with simple neural dynamics. So they are agents that have very simple neural dynamics that enable this sort of closed-loop feedback from the environment. We equipped our agents with a model of minimal neural dynamics based on the coordination dynamics framework. We talked about coordination dynamics a little bit, but this is the framework that J.A.S. Kelso developed, and then it's been refined through sort of thinking about cognition as a complex dynamical system, maybe instead of information processing. And so this is a different perspective on cognition, and coordination dynamics is where you coordinate, different things like neurons or agents, and you are basically coordinating oscillators. And we talked about that last time about oscillations and coordinating oscillations and how there's a history of that in chaos and complexity theory. We talked about how that actually goes back to Norbert Wiener, maybe. And so this is just another way to kind of think about cognition. So we have this minimal neural dynamics based on the coordination dynamics framework, and then embedded these agents in an environment with a stimulus gradient. So a stimulus gradient is where you have like a source and it decays over space, and your agent is exploring the gradient to go from like low concentrations to high concentrations. And they do this in space and of course in time because it takes them time to move across the gradient. If the gradient diffuses, there's a time course for the diffusion of the gradient, and so forth. So you can do a lot of interesting dynamical systems modeling with a stimulus gradient and an embodied agent. In our single agent setup, the decision between two stimulus sources depends solely on the coordination of the agent's neural dynamics with its environment. In our multi-agent setup, that same decision also depends on the sensory motor coordination between agents. So you have this interesting coordination dynamics framework where you're coordinating the environment and the minimal neural system in one agent. And then you have multiple agents that are exhibiting parallel behaviors. They're all sort of exploring this gradient. They all have this coordination dynamics pairing between the environment and the agent's minimal neural system, but then each minimal neural system is coordinating with themselves. So it's a bit like when ants explore a pheromone trail. Ants will lay down, like they'll explore their environment, they'll lay down a pheromone trail. Other ants will kind of move towards that pheromone trail and reinforce it. If they find that, if there's like, say, like food on the other end of it. So their collective behavior, they kind of interact with the source, which is the food. They form an initial trail to the food of pheromone, and then other ants will pick up on that pheromone scent, and if they can confirm that there's food on the other end, but through their own sort of neural processing, they then lay down more pheromone, and that signal gets reinforced, and then other ants will follow that signal and keep reinforcing it. So there's this interesting relationship between sort of coordination of behavior, and there is actually a reinforcement learning aspect here, which we're not talking about, but that's just kind of what's going on here. They don't really imply, but they imply it, but they don't talk about reinforcement. Okay, so in our multi-agent setup, the same decisions also depend on sensory motor coordination between agents via their simple social interactions. Our results show that the success of collective decisions depended on a balance of intra-agent, inter-agent, and agent-environment coupling, as I mentioned. There are these different types of interactions that are all important. And we use these results to identify the influences of environmental factors on decision difficulty. So, we have this, how, depending on how difficult the decision is, these different factors influence it more or less. More generally, our results illustrate how collective behaviors can be analyzed in terms of the neural dynamics of the participating agents. This can contribute to ongoing developments in neuro AI and self-organized multi-agent systems more generally. So in this paper, of course, they're talking about collective decision-making, and what they're getting at is this consensus idea. So we talked about consensus with the Habermas machines, and that's one way to do this. This is in agents, embodied agents, where they're trying to develop a consensus about the environment. So where are the resources? How do we behave? How do we reinforce each other's behavior to find sort of a consensus solution? So every group, could be embodied agents, it could be ants, it could be people. You have to have these consensus decisions. And so collective decisions that are made by the group itself without external intervention, meaning that there isn't some agent or force telling them what to do, typically requires that a consensus emerge in the group. Consensus entails that all or at least a large majority of individuals agree, either on an approximate continuous value, for example, a position in continuous space, or a discrete option, such as voting for an arbitrary item from a list. So it's like, basically you have to have this reinforcement of the pheromone trail. You have to have an initial sort of hypothesis about where the source is, and then other members of the population verify that that decision, that hypothesis, and they reinforce it, and eventually it becomes sort of the consensus view. There may be resources in other places, but that's the most reliable path to a resource. So this gives it eases cognition in the sense that it makes the decision process easier. You don't have to run through all the options every time you want to find a path to food. You have the path laid out, and it results from this sort of self-organized sort of exploration decision making. because there's no top-down decision making here. This is all from just the agents interacting. Consensus is achieved in this way through a distributed process that is not under the control of any single agent. Multi-agent models have been instrumental in investigating how the distributed interactions of individuals can result in a consensus. Individual agents used in most models behave according to rather simple rules or heuristics. So in opinion dynamics models, agents typically update their opinions according to the majority or to the voter rule. Some recent models aim to replicate human cognitive processes more closely by using neuro-inspired approaches, such as the drift diffusion model. So this is a model in, I think in diffusion models. It's a class of diffusion model, and I think we talked about that in this group as well, where this is kind of a neuro-inspired approach to this type of cognitive process. So this is an interesting type of cognitive process that, again, is not directly based on information processing. It's this sort of physics analog. These opinion dynamics models have greatly advanced our understanding of how peer-to-peer interactions can give rise to collective phenomena such as polarization or consensus. So this is, applicable to opinion space or physical space. So, if we think about how animals choose a new nest site, or humans find an exit during an emergency evacuation, we can use these type of models as well to find that consensus path. Also, in these more embodied models, behaviors are typically governed by simple rules or heuristics. These models have been illuminated, for example, how animals can resolve differences in initial movement direction and move towards a single location using only local implicit communication. So their approach to this is a little bit, it's very minimal embodiment. So they're not drawing very heavily from the body part of embodiment. It's just kind of like it's in a space, it's in an environment, it's in a context. Okay, so this is where they kind of get into coordination dynamics. In the interest of time, I'm not going to get deeply into that. I'm just going to kind of outline it. So they actually do mention 4E cognition here. So considerations of the brain-body environment interplay have gradually permeated cognitive science, culminating in the 4E cognition framework, which sees cognitive processes as being embodied, enactive, embedded, and extended. And so they kind of bring that up. And then they start to talk about coordination dynamics. So, there are all these challenges to understanding sort of the brain and sort of, thinking about cognition, not necessarily as information processing, but as a complex system. If you want to operate successfully in an environment and you have neural activity, you have this sort of bio-inspired model of the thing that's driving the behavior in the environment. The biological agent must be attuned to characteristics of the environment. In neuroscience, brain activity is typically studied in terms of oscillations. So this is where we get into neural oscillations. We talk about different rhythms that are generated by those oscillators and how that leads to synchronization with the environment, and how brain rhythms can rapidly shift to accommodate changing environmental tasks and environmental demands. So this is like kind of framing this in this oscillatory framework and how a bio-inspired model really is based on these sort of oscillators that are entrained or become entrained. And so this brings us then into coordination dynamics, because coordination dynamics really kind of came out of this idea of oscillators as being the drivers of behavior. So a lot of the stuff in coordination dynamics originated from either movement studies where they're like moving, trying to synchronize their body movement, their finger movements to a metronome, or studies of fMRI where you're looking at synchronization of different brain regions during cognition. So this is kind of, and coordination dynamics is based on a physics model we'll talk about in a minute, but it's been widely used to study how the activity of these dynamically interacting components is coordinated. So one advantage of the coordination dynamics approach is that it can be used to study the metastable regime in which the brain usually operates. So there's this focus in coordination dynamics on metastability, or these points of stability that are sort of poise the brain towards going into one of two states or one of multiple states. So one advantage of like looking at cognition in this way is that you cannot just, say that something is a result of information processing, but by saying that sort of the brain is poised to take advantage of different behavioral regimes at any one time. It's metastable with respect to different behavioral regimes and these different aspects of the environment and interacting with other agents can kick it into one of these others, one of these different states. So that's kind of the idea here. And so, this allows us to model the dynamics of a system. So the system goes from metastability to going into one state or another and then returning to metastability. And then you can look at the trajectory of that to see what states the brain visits and, over time. So you can actually look at whether the dynamics are stable or unstable, whether the brain is being overwhelmed by environmental input, and how that plays a role in preventing or facilitating adaptive behavior. So this is another part of their embodiment, is that they're looking at the agent's minimal neural system as a set of oscillators that are synchronized and that have these dynamics that are, allow us to describe how it synchronizes with both its environment and its other fellow agents. So a metastable regime resolves the problem of sort of being stable or unstable by allowing the brain to dynamically switch between several stable oscillatory states, thereby being neither completely stable nor completely unstable. So it sort of balances out stability and instability, and it does this over time. So it gives us a new way of thinking about cognition, not as like this information processing machine, but as this dynamical system. And so the Haken-Kelso-Bunz equations, the HKB equations, are sort of the way that we modeled this metastability. And it's this, it basically comes from physics. It comes from looking at stability in physics, where you have metastable states and you have stable states. And the metastable state is up at the top of a energy well, and then the system will go down into one energy well or another. You'll see these metastable diagrams. I don't know if they have one in here, but usually the system is poised at the top of a hill, and then it can go down one side of the hill or the other into these stable states, which are these basins of attraction. And then, of course, it can be poised back up at the metastable state, ready to go into another state's well, and so on and so forth. So that's kind of a qualitative description of this. Two oscillating components, when modeled with the HKB equations, show in-phase attraction, similar to the Kuramoto model, which we talked about last week, and also anti-phase attraction, which is another behavior. The simultaneous existence of in-phase, so-called symmetrical, and anti-phase, so-called asymmetrical attraction, produces a simple form of metastability. So you can have metastability by having these entrained oscillators. They can be in phase or anti-phase, and sometimes you can have both. So this is really kind of a good, I think, way to think about some of these stabilities and instabilities in cognition. It's definitely different from the information processing approach. And of course, it's going to have consequences for how we might think of compositionality. If, I mean, compositionality might be possible in this model. I don't know if people talked about it or thought about it, but it's going to be a very different way to achieve it. In studies of continuous collective decision making, an oft-studied question is, under which conditions can agents with different preferred movement directions reach a consensus? So in this model, they're actually just looking at the movement direction of an agent. And the oscillators are controlling that movement direction. And as they communicate with each other, they all reach a consensus about which direction is best. So, you might have a population of 1,000 agents, and they're all pointed in slightly different directions. And so you could just simply take an average of those agents and look at how their direction changes over time. And over time, what you should see is that the average direction should even out to some average that has a very low standard deviation, and that this happens where you basically destroy a lot of the wildly different directions, and the directions that are kind of close but not really where they need to be get aligned to each other. So this is, and we can think about this in terms of this dynamical systems model by saying, that there's certain states that are going to be more likely to be achieved. So let's see if they have a model of gradient descent and decision making here. They show the agent architecture first of all, where they show these 4 nodes, and they have this fully connected network. They have sensory inputs coming in, and then they have some output of motor control. So they have this motor oscillation from the inputs processing through this very simple network, and then they have this angular displacement, which is the angle or the direction of movement. And so as it's monitoring the gradient, as it's monitoring its neighbors, it's processing this through the network, and it's producing this angular displacement, which is the angle of movement. And so that angle of movement should become aligned over time. And so this just shows gradient ascent, which is ascending that gradient, that sensory gradient, towards the greater concentrations. It kind of ascends in a linear fashion until it gets near the apex, at which point it kind of explores that apex or near the apex to make sure that it's hit the global optimum. In decision making, when you have 2 options, when you have 2 stimulus gradients that kind of overlap, you have to make a decision between one source or another source. So in this case, there's kind of this line down the middle, and then the agent veers off towards this option, exploring this gradient linearly until it reaches near the global optimum, explores that for a while, and then hits the global optimum. And then this shows the brain dynamics, or the dynamics of this network, and it shows the sensory motor left, the sensory motor right, and the motor-motor connections. And then those are all kind of plotted out here, where you have this, basically over time, you have this variation. So as it's making this linear move towards the gradient and up the gradient, the brain dynamics are sort of, all the same. And then when it starts to make this exploration move, when it starts to kind of wander around the global optimum, that's where you get these these highly fluctuating dynamics. And so then this shows where you have successful and failed consensus. So a successful consensus is where the entire population aligns and moves towards one option or another. A failed consensus is where you still get different parts of the population going to different sources. This is reflected in the movement dynamics, which is the agent orientations and how those separate out, and then the brain dynamics, which actually show intra and inter-agent brain dynamics. And so the brain dynamics separate out as well. Or actually, in the case of this failed consensus, they converge, and in the successful consensus, they diverge. Which, I mean, I could go into the paper a little bit more, but in the interest of time, we will not. But just put a marker in that. So, okay. So I think that's it for that paper. I think it's a pretty interesting paper. A lot of interesting things, especially with respect to embodied agents and modeling cognition.
Yeah, I mean, yeah, Dumas always has the coolest papers.
Yeah.
Really interesting. Really interesting. Gonna need to play with that. Like, anyway, and blast from the past to see Kelso.
Oh, yeah.
People talking about Kelso. Dumas is on a roll this year. I don't know. Anyway, he just got a grant on quantum machine learning and neuroscience agents. Something. And definitely, like building on Qiskit, like coding quantum computers for fun and profit. Looks super interesting, and I'm just trying to remember. Anyway, there's another project of his that is also super interesting. So just to see this, I don't know how I missed this this particular paper, but
I think it was it in the Slack or not?
I don't. It could be, but I have not gotten into it, and yeah, great stuff.
Yeah, good. All right, well, I think that's it for today. Thanks for attending. It was a great meeting. See you next week.
Take care.
Take care.
Bye. See you.
Bye.
Bye.